So, let me summarize what we have done so far. We have said that if particles or electrons are moving in a periodic potential, then the wave function satisfies the form, it has the form e raised to I k x u k x, where u k x is periodic, u k x plus a. This is known as Bloch's theorem. Keep in mind, when I write Bloch, it is B L O C H. A lot of people make a mistake of writing as B L O C K. It is B L O C H. Second thing we did is nearly free electron model for weak periodic potentials, so that we could use perturbation theory. For this, what we did was wrote V x equals as phi 0 plus summation g not equal to 0 e raised to I g x times the coefficient phi g, and took this V 0 to be 0, and therefore, the first order change in the energy comes out to be 0, and what mattered was the second order energy change. Just a bit about notation. I have been little careless in writing the notation. I have used things like e raised to minus I k prime x, whatever the V is, e raised to I k x. Actually, what this refers to is the matrix element k prime V k, and the space representation of k prime is e raised to I k prime x, and therefore, space representation of k prime x becomes e raised to minus I k prime x, and this is what I have used directly in writing my matrix elements. In case you wonder, I just wanted to clarify that. So, I will be using this back and forth, just follow this as it is. So, back to second order energy change, which we found to be equal to summation g V g mod square over E k minus E k plus g, and this is energy change for the kth level. Let me just go over this calculation once more, so that you are very clear about the normalization and things like that. Remember, the 0th order wave function psi 0 x is 1 over root L e raised to I k x, this is psi k x, and when I take the expectation value k prime summation g V g e raised to I g x k, it turns out to be 1 over L integral e raised to minus I k prime x, there is a V g here, e raised to I g x e raised to I k x dx, and this is nothing but V g over L integral of e raised to I k plus g minus k prime x dx, and this integral is over the length over which the periodic boundary condition is applied. Therefore, this is equal to 0 if k prime is not equal to k plus g, and it is equal to integral of dx over L when it is equal to k prime is equal to k plus g. So, this you can write very easily as V g delta k prime k plus g. This is what we used earlier. So, I just wanted to clarify how it is obtained. In any case, E second order then comes out to be summation g V g square over E k minus E k plus g, and I will put a 0 on top to show that these E k and E k plus g are being calculated at unperturbed level, so that the total energy of the system for kth level, I will put k here, is equal to E k 0 plus E k 2. Remember, the first order is already taken to be 0, because that was just the background constant shift of the potential. Now, when I plot the total energy E k, with respect to k, E k 0 is parabolic, and when I add the second order energy to it, it will have some value near k equals 0 and around it, but the main point is that when I come to k equals pi by a or k equals minus pi by a, what happens then? And let me show this on the side. On the right hand side, I will show when k equals pi by a, and if I take g equals minus 2 pi by a, then E k equals E k plus g, and therefore, let me put a 0 here. The denominator here becomes 0, and therefore, E 2 k blows up, it becomes infinitely large. Let me show it for k equals minus pi by a also. If g equals 2 pi by a, then E k 0 becomes E k plus g 0, and again we see that the denominator blows up, E k 2 becomes infinitely large. That cannot happen. Where did we go wrong? Where we went wrong is that at these k's, the k's at the Brillouin zone boundary, when E k 0 is equal to E k plus g 0, the energies are the same. The two levels E k and E k plus g are degenerate, and when we calculated E k 2, we used perturbation theory, which is applicable only to the levels when they are not degenerate. So, to calculate energy at these points, I must use degenerate perturbation theory, then only I will get the right answer. So, we will do that now. So, what we have figured out by looking at E 2 is that, let me make this E k 0 again. What we have figured out is that near k equals minus pi by a and pi by a, the levels become degenerate, and therefore, I cannot apply the perturbation theory, non-degenerate perturbation theory that I used. Same thing would happen at any Brillouin zone boundary or any multiple of these k's. So, even at k equals minus 2 pi by a or k equals 2 pi by a, again we will have a g that will have energy level degenerate with k plus g, and we have to apply degenerate perturbation theory. And let us see now what happens when we do that. To apply theory, we will consider only those levels which are degenerate. Why? Because other levels are far away, so they are not going to have effective mixing at the 0th level. So, we will consider only those levels that are degenerate. So, at k equals pi by a, we will consider levels k equals pi by a and k equals minus pi by a. Similarly, at k equals minus pi by a, we will consider k equals minus pi by a and k equals pi by a. These are the levels which are degenerate, because energy depends on k square and k is equal to k plus g. So, how do we apply degenerate perturbation theory? What we do is, so I have two levels k and k prime which are degenerate, and that means that E k equals E k prime. Given the Hamiltonian, which is h 0 plus V x, which is minus h cross square over 2 m d 2 by d x square plus this summation g V g e raised to I g x. I will consider only two levels k and k prime. What we do is, if the energy of the states formed by making linear combination of k and k prime is E, then I should have H, the linear combination psi equals E psi. Let us see what does it lead to. So, I make a linear combination psi which is equal to some constant A k plus B k prime, and let me write this as A k plus B k prime I know is k plus G for some G, G could be 2 pi by A, minus 2 pi by A, whatever, wherever the degeneracy is there. Then if I take H 0 plus V x acting on psi, it gives me E psi. Then what do? We write H 0 plus V x acting on A k plus B k plus G is equal to E times A k plus B k plus G, and that gives me A E k 0 when H 0 acts on k times k plus A V x k plus B E k plus G 0 k plus G plus B V x acting on k plus G is equal to A E k plus B E k plus G. This is the working equation for the second order perturbation theory. From this, I will once take the expectation value with respect to k and once with respect to k plus g, and I will get two equations. Let us do that now. So, the equation I am working at is A E k 0 k plus A V x k plus B E k plus G 0 on k plus G plus B V x k plus G. So, this whole thing is equal to E A k plus E B k plus G. If I take the expectation value or multiply this by bra k, I get A E k 0 plus k V x, k gives me V 0 which we have taken to be 0, plus k plus g, inner product is 0 and I get plus b k Vx k plus g is equal to a e, which I can write as a e k 0 minus e plus b, and this expectation value would be v g. Let us see, k should be equal to v, it will be v minus g is equal to 0. Similarly, if I take the expectation value k plus g, I will get b e k plus g 0 minus e plus a v g is equal to 0. Let me rewrite this, bringing a first. So, I will rewrite this as a v g plus b e k plus g 0 minus e is equal to 0, the same equation. So, I have equation, this is my equation number 2, this is my equation number 1, and if a and b have to be non-zero, the determinant of the coefficient must vanish, and therefore, for a not equal to 0, b not equal to 0, I should have e k 0 minus e, v minus g, v g, e k plus g 0 minus e mod square is equal to 0, and that will give me the energy eigenvalues. Let us see what these are. So, I have to determine energy eigenvalues E k 0 minus E V minus G V G E k plus G 0 minus E is equal to 0, and this gives me E k 0 minus E k plus G 0 minus E minus V G times V minus G is equal to 0. Recall from earlier, because of the reality of V x, we have V minus G equals V G star, and therefore, this equation becomes E k 0 minus E k plus G 0 minus E minus mod V G square is equal to 0. This is a quadratic in E, and therefore, it gives me 2 eigenvalues. So, let us now look at that, what it gives me. It gives me, since E k 0 equals E k plus G 0, this implies that I get E k 0 minus E is equal to plus or minus V g, or E equals E k 0 plus or minus V g mod. So, let us see, when I solve this, E k 0 minus E V minus G V g E k plus G 0 minus E equals 0, and taking into account that we have E k equals E k plus G at the 0th level, I get E equals E k 0 plus or minus mod V g. That means, I get 2 eigenvalues. So, if I will go back to that curve which I had plotted at 0th level, which was E k 0, and we had problems at pi by a and minus pi by a, the energy actually is not equal to this h cross square k square by 2 m at these 2 eigenvalues, because these 2 k values, because energies are degenerate. What happens instead is that this energy starts deviating and goes low. This energy starts deviating and goes low. Whatever I have done here for k, it applies equally well to k equals pi by a or k equals minus pi by a, taking appropriate g. And the other eigenvalue opens from the top, and this energy becomes like this. This energy becomes like this. Other places it is not affected. So, now I am going to erase the middle thing and show you what the energy structure now looks like. I am going to erase this part and plot the energy like this, and it opens up here and again goes on top, where this gap is 2 v pi by 2 pi by a mod. This gap here also 2 v 2 pi by a mod. You can show similar thing for other case where they are near the Brillouin zone boundary. So, what have we learnt in nearly free electron theory? Periodic potential V x equals summation g not equal to 0 V g e raised to I g x plus V 0 we have taken to be 0 because this is a shift in the potential opens a gap in the energy at k equals plus minus pi by a. It will also open it at plus minus 2 pi by a, because I can add g equals 4 pi by a and get degenerate eigenvalues, and so on. So, now the energy eigenvalues are no longer continuous, they are discontinuous at Brillouin zone boundaries. So, there exists a forbidden energy region or a energy gap or a band gap at Brillouin zone boundaries. This is the conclusion of this lecture. We will make it more rigorous in coming lectures. Thank you.